This video goes over vertical expansions, compressions, and reflections. So the first thing that we're going to do is compare 4 different parabolas here. So the first one I'm going to draw on is y equals x squared. Second one that I'm going to draw on is y equals 5x squared. If I do kind of a quick table of values, I know that if my x is -1, my y value is going to be 5. If x is 0, y is 0, and if x is +1, then y is +5. So I'm going to plot this one in blue, and I can see that I've got a much skinnier parabola than I had before. The next one that I'm going to take a look at is 1/10 x squared. And if I visualize a table of values again, I'm just going to have it much flatter than before. And I've got y equals 1/10 x squared. And the last one that I have is y equals -5x squared. So again, visualizing my table of values, I'm going to have it the same width as y equals 5x squared, except I'm going to have it opening down. So those 4 summarize the effects of this A value on a function. And so we're going to look at another example right here. So my blue grid on the graph right here, this is f at x. What I'm asked to do is graph y equals 2 f at x and y equals 1/3 f at x. These are vertical transformations, so they are only going to apply to the y coordinate. So I'm going to read off the x values that I have here. So -4, -2, 1, and 4. And then I'm going to read off my y values. So -1, 2, 0, and 1. And then I'm going to apply my transformations. So my first one here is I'm going to take 2 and I'm going to multiply it by f at x. So I get -2, 4, 0, and 2. On my third column, I'm going to take my original y values and multiply them by 1/3. So I get -1/3, 2/3, and 0. And finally 1/3. So now what I'm going to do is I'm going to plot those two. I'll do red first. My x coordinate is the same. My y coordinate is different. And then I've got -2 and then 4, 1, 0, which is called invariant because it stays the same. And then 4, 2 right here. So then using my ruler, I'm going to connect those lines. And what we can see is that kind of like the parabola, I was multiplying by a whole number. And so I've actually stretched my graph vertically. The peaks became taller and the valleys became a little bit deeper there. Okay. So my next one I will do in green here. So now I'm taking my original x coordinate, I'm plotting it with this new y coordinate. This one is going to be a vertical compression. So I've got, let's see, -1/3, which is probably about there. Then I've got -2 and 2/3, which is probably about here. Same invariant point. And then I've got 4 and 1/3 here. So again, connecting my dots. And now what I can see is that I've got a vertically compressed graph there. So an invariant point is the last thing that we have on there to define. And an invariant point is just a point that remains unchanged. Okay. So let's summarize what we have here. In general, y is equal to a times f at x. And so if that parameter is greater than 1, the function let's say stretched vertically by a factor of a. If a is between 0 and 1, so a fraction, the function is going to be compressed vertically by a factor of a. So if a is less than 0, the graph is also going to be reflected in the x-axis, as we saw in our first example with the parabola. Okay, so now we're going to do some examples. So for each function below, we're going to identify the parent function, state the transformations, do domain and range, and then identify any invariant points. So here we've got y equals root x is our PF, our parent function. And to sketch that, I'm going to draw a couple points here, 4 and 2. And that is my parent function. Now my transformations that are happening here is I've got a vertical stretch by 3 because I'm multiplying by a whole number. That is a vertical stretch. And then I'm going to graph that. So the points that I chose for my original function were 0, 0, 1, 1, 4, 2. And my y was 0, 1, 2. This is applying to my y coordinates. So when I apply that transformation, I'm really just multiplying all of my y coordinates by 3. So 0, 0 stays the same. 1 times 3 is 3. 2 times 3 is 6. That's going to allow me to now plot those 3 new points on my grid. So 0, 0 is the same. 1, 3. And then 2, 6. And then I've got this very steep function here. Oh, I actually have a mistake there. It should be 4. Maybe you identified that already based on what I said, but this should be 4 here, and 2, and then 4 and 6. Then our shape looks a little bit better. So I've got 1 and 3, and then 4 and 6. And now I can see that I've got my vertically stretched function. My domain of this new function is actually the same as the parent function. So I've got from 0 to positive infinity, which is the same as the range, 0 to positive infinity. We have one invariant point, which is 0, 0. Okay. And then the last thing that we're going to do before we move on to our next example is just graph a reflection and write an equation. So if I'm graphing a reflection, I know that my a value is going to be negative. And then that would be my new equation. What that reflection means is I'm going to take each of my points and make them negative. So I've got 6. And then I've got a reflection here. If you're using a table of values, it would be like multiplying all of your y values by negative 3 instead of positive 3. Let's do another example here. I've got y equals 5 over 2 x squared. So my parent function, or PF, is going to be a parabola. So y equals x squared. And I can sketch that on my grid. Next thing I'm going to do is identify my transformation. So my a value is 5 over 2. So I actually have a stretch by 5 over 2. And so then the next thing that I'm going to do is make my transformation. So I'll write down my table of values, and I'm going to choose some points here that are easy for me to work with. So let's choose -2, 0, and 2. And then my y value is going to be, on my original parabola, would be 4, 0, and 4. My transformation in this case only applies to my y coordinates. And my transformation is a stretch by 5 over 2. So I'm multiplying each point by 5 over 2. So here I would get 4 times 5 is 20, divided by 2 is 10. 0 stays the same, that's an invariant point. And then 4 times 5 is 20, again, divided by 2 is going to be 10. So plotting those points, I've got -2, 10, 0, 0, and then 2, 10 on the other side, which is going to give me a much skinnier parabola here. So I've got y equals 5/2 x squared. I have one invariant point, which is 0, 0. And then I'm going to state my domain and range. So my domain hasn't changed from my base parabola. I can have any x value from -infinity to positive infinity, and my range is going to be the same as well. I can have any value from 0 to infinity. The last thing I'm going to do, just like above, is graph a reflection of the function in the x-axis and write an equation. So I'm going to reflect it. I know that that means my points are just going to become negative. I've got it reflected now, so I can write my equation, which is the exact same, just with a negative a value instead of a positive one. This doesn't really apply to this, so we can leave that out for now until we get to the stage where we are combining transformations.